Hi, this is Miss Wenslav. Today I will be reviewing 1D forces. In this lesson, I'm going to cover basics of forces, and I will also go into specific scenarios. One of the most important parts about forces are force diagrams. We also call these FBDs, or free body diagrams. These images represent all the forces that are acting on a system at a given time. This may also include actual numbers that represent forces in different directions. We have a few different types of forces that are going to be important to us. First, we have normal force. This is support force. And this is always perpendicular to whatever the object is sitting on, which I'll show you an example in a moment. Applied force is anything pushing or pulling on an object, and this may actually have a number attached. Spring force is with a spring. Gravity we always have is 9.8 meters per second down. Tension is when we have a rope. Air resistance when something is traveling through the air. And finally friction, which is typically opposite of movement. All these forces will be coming back to throughout this unit, so if we don't really go over all of them now, they will be coming back later. Our example, a rock is dropped into the sand and creates a small crater. So while this is through the air, we have gravity pulling down, and then we have a tiny bit of air resistance going the other way. Now you'll notice that the size of my arrows really represent how much force is acting on it. In this situation, we know that gravity has a lot to do with what is pulling this rock down. Now as it drops into the sand, so if we have our rock here, we still have gravity down, but we also have that normal force going the opposite direction. So like I said, normal force is always perpendicular to the force or whatever the object is sitting on. So if something is on an angle, the support force is still perpendicular. This is going to be really important in our second part of this unit. So when we're adding and measuring forces, it's almost exactly how we looked at vectors. Objects, if they're going in the positive, are positive, and negative are negative. So we would have 5n minus 3n equals 2n. Now, just as a note, if I had forces also going in the x and y direction, let's say they were 5 newtons and 4 newtons, the same type of thing would be going on. This would be in the x direction, and then I would have my y direction. So I would have 4 newtons, because it's positive, minus 5 newtons. So that'd be negative 1 newton. My next step could be creating a triangle to solve for the vector. So a lot of these vector parts of our first chapter are going to come back in this unit. Okay, so if we think about motion and forces, they are really closely tied. So a lot of the standards we had from last unit are going to come back in this unit. So for motion and forces together, we have a few different situations. First, if an object is at rest, that means all the forces on an object are equal. Now, if we have an object at a constant velocity, we actually have the same free body diagram. So all the all of the forces are equal, except we have some average velocity as this thing travels over time. So this is going to be kind of important to us because our forces are equal, whether it's at rest or at a constant velocity. And when we talk about Newton's first law in a moment, we'll see the connection. Now, when we have an object that's slowing down, we have to have some external force on that object. So in this case, if it's slowing down, we need to have some force that's opposite of that object. However, an object is speeding up, we need a force pushing it in that positive direction. So it's important to think about in these problems whether an object is at rest or at a constant velocity, that means everything's equal, or if it's slowing up, speeding down, accelerating. That means something else is going on, and there has to be some external force causing it to do that. Okay, so I'm going to go over Newton's first laws and their application to this unit. So first, Newton's first law, an object stays at rest until acted on by an outside force. Object stays in motion until acted on by an outside force. So exactly what I was just talking about. If I have an object at rest, that means all of my forces must be equal. However, if this object is moving, that means I must have one force that is greater or less than the rest of them. So during this unit, it's important to think about every time we see a situation. Okay, is everything equal? Is it at rest? Or is it accelerating something else going on? Okay, let's now talk about Newton's second law, which is our big equation for this unit. You've typically seen this as F equals ma. However, you'll notice on your equation sheet, so take a moment to grab that and look at it, it is written a little bit differently. We rearranged it as A equals the sum of F over m. Now, this is important. This sum means that's all forces. All forces, whether it's in the x or the y, on that object. Let's try a problem to think about what's going on. So a suitcase has a mass of 10 kilograms, and the earth exerts approximately 100 newtons on the suitcase. You exert a force upwards of 120 newtons. So right here, I'm pulling it up with 120 newtons, but the earth is pulling it down 100 newtons. If the suitcase starts at rest, how fast is it traveling after lifting it for 5 seconds? So this is pretty important. If I look at my free body diagram, you'll notice that they're not equal forces. So we know that this particular thing is accelerating. Okay, so let's use our equation. So I know A equals the sum of all forces over m. Now I'm looking for A. We know this thing is moving, so I have to be looking for that. A is my way to figure out, okay, what is the motion that's happening in this situation? So I have 120 newtons up, and then I have 100 newtons down. And I have that over 10 kilogram, which I got from my problem. So doing some math, this is going to give me 2 meters per second squared. Now at this point, I can start figuring out how fast is it traveling after 0.5 seconds. So let's write down things that I know. I know my time equals 0.5 seconds, velocity initial equals 0, and we figured out my acceleration at 2 meters per second squared. And we are looking for velocity final. So at this point, I have done everything new, and now I'm just going back to things that we've already done before. So looking at my equation sheet, I'm going to use this equation, plus AT. Velocity final is already solved for, so velocity final, after I plug in my numbers, is going to be 1 meters per second. So Newton's second law really brings together forces in motion from last unit. Okay, so the next thing I want to talk about is gravitational forces. So we know that F equals ma. We just went over that. Even though we write it differently, I'm going to start off with this. Now, this force, as a reminder, this is measured in newtons. Okay, so if we're thinking about weight, well, how are we going to figure out weight? Well, weight is going to take our mass and then times the acceleration that is always acting upon us, which is gravity. Now, it's important to remember we're going to keep G positive. Why? Because we're going to be using the force that we're figuring out, whether that's weight or a regular force, as a vector. So remember to keep G positive in this unit or you may get a little bit confused. Okay, so the next thing we're going to talk about, and we're also going to do this lab in class, is elevators and forces. So this is sometimes kind of difficult to understand, go through the math, so we're going to be spending some time really focusing on what this means. So let's say you're standing on a bathroom scale in an elevator, and you're making trips up and down this elevator. So when you start, your mass is 50 kilograms, and when you stand on the scale, it reads 490 newtons when the elevator is not moving. So if we're using terms like weight, this is our weight, but this is also the force of the earth on us. All right, so we're going to talk about how we go through and solve some of these problems. So first, what would the scale read when I have an upward acceleration of 1 meters per second? So that means that my elevator is accelerating up. Okay, let's figure this out. So we have A equals the sum of F over M. So that's our fancy way of writing Newton's second law. Okay, so we have two forces acting. We have the force of the earth, and we have the force on the scale, and that's all over M. Now we know from our previous slide the force on the earth is always our mg. Now this is negative because my weight is going down, plus my scale over M. Now this is pretty important to us at this point because I need to figure out the force on the scale. So you might be saying, well, we already know the weight. Well, we know the weight of that person when it's not moving, but when it is moving, something's different going on. So we're going to rearrange this equation to solve for Fs. So let's multiply m on both sides. Oops, I lost my pencil. Okay, there we go. M. So we're going to have m times a equals negative mg plus Fs. Remember, Fs is the force on the scale. Let's rearrange for force of the scale equals m times a, mass times acceleration, plus mg. So this is going to be our guiding equation throughout this problem. So we have an upward acceleration of 1 meters per second squared. So we're going to use this equation that we just solved for, which as a reminder, if Fs equals mass times acceleration plus mass times gravity. So at this point I can really plug in my numbers. So my force on my scale is equal to my mass, which is 50 newtons, times 1 meters per second squared, plus my mass times gravity, which they gave to us would be 490, but we could also solve that ourselves. So this would give us, when we have an upward acceleration, our weight on our scale is actually more. Now in the next situation, it talks about, okay, let's say that we are at a constant velocity, so velocity is constant. If I have a constant velocity, this means acceleration is equal to 0. So if I use the same equation as above, so that's this guiding equation, I have my mass times 0, no acceleration, plus 490. So that's still going to be 490. So this is important. If my scale is reading the same amount, my normal weight, that means that that elevator is either not moving or in constant velocity. And lastly, if we have an acceleration of negative 1 meters per second squared, you may be able to predict what's going to happen, but my force on my scale is still mass times acceleration. So that's going to look like 50 times negative 1 plus 490. So this is going to give me 450 reading on the scale. So our last concept is Newton's third law. So forces come in pairs. So when we're looking at forces, it's important to remember that if I have something going on one side, probably have something else going the other side. So this is going to be really important when something is at rest or constant velocity, if we're thinking about everything acting on an object. So thank you for listening to this flipped lesson. If you are one of my students, make sure that you fill out the Google form and come prepared to class with your notes.